Hello, in this video we're going to generalize work to 2 dimensions and 3 dimensions. We'll do our example in 2D just because it's a little bit quicker, but everything we say will work just fine in 3 dimensions. You'll also, as a side effect, learn what a line integral is and how to do easy ones. So, actually, let me start with work here. So work is equal to an integral of f dx as we go from x initial to x final if we're working in 1D. So what's different about 3 dimensions is instead of dx we need something like a dr to be our vector for us, and we need to take care of the fact that this is actually a dot product. So what we're going to get in 3 dimensions is that work is equal to the integral f as a vector dotted with dr, which is a vector. And instead of having just an x initial and x final, we are in principle making some kind of path as we move through space. So just to make a 2-dimensional sketch of this, let's say we have our x-axis and our y-axis, which should actually touch each other. Okay. And let's say we have our force F going from some initial point to some final point. It's a plot of F. And somewhere along there, as we move along this path, we have a changing direction. So at this moment, our direction, our dr would say point like so, and F has some direction, let's just say it points like that. And as you integrate, so as you move from your initial point to your final point along your path, dr is always pointing along the path because that's the direction you're going. F is pointing wherever it happens to be pointing. And so F is a function of position. So instead of having just an x initial and an x final, because we also have a y initial and y final, the way we do this is we have some kind of path, which we would specify if we knew more about our problem, but generically we just say it's some path. Okay, so that is a line integral. It's because you integrate along some line, some path, instead of integrating along an axis. And that's mid-level math. I mean, it's probably, I don't know, maybe you've seen these already, or maybe you haven't. In any case, they're really not so terrible. Let's just talk about how to do these, not because I'm going to make you do a bunch of line integrals, but because it's good for understanding what work actually is. So working through these, step 1 is always going to be to just apply the dot product. And I see my little letters dancing around. Oh, because I'm still in crazy mode. All right. Well, I guess that's still legible. So step 1 is to apply the dot product, and that might be all you really have to do. After that, it could just be a normal integral. So for example, let's look at where that would be the case. Let's say we have our force equal to 4x I hat plus 3y squared j hat, and that's acting on some particle. As it moves from point 1, 1 to point 3, 4 along some path, which I actually don't even need to specify in this case. If it really bothers you, we'll just say it's a straight line. And for the sake of units, we'll say F is in units of newtons, and x and y are units of meters, and these constants have whatever units they need to make everything work. So if we calculate the work, that's these 2 vectors dotted with each other. Okay, so let's do that first. The force vector is equal to 4x I hat plus 3y squared j hat. And we want to dot that with dr. If you're wondering what dr is, dr, we should put that somewhere. Let's do it in red because I used it red in this sketch here. The vector dr is always going to be equal to dx I hat plus dy j hat plus dz k hat. And the reason for that is it's telling you about the direction you're going. You go a little bit in the x direction, a little bit in the y direction, a little bit in the z direction. That's your dr. Okay, so we put that in here. We're only going to need the x and y components because this is a two-dimensional problem. So we could say dx I hat plus dy j hat. If you think I'm cheating by leaving off the dz k hat, you can put it there if you want to, but immediately once we do this dot product, there's no k component over here, so it doesn't do anything. Alright, let's work out what that dot product gives us. It's going to give us 4x times dx, and it's going to give me, we'll add 3y squared times dy. Okay, so that's all the dot product does. It turns this f dr into the x component times dx plus the y component plus the dy. In fact, we might even want to write that sort of, we'll squeeze it in over here as an intermediate step, because it always gives you this, fx dx plus fy dy. Okay, so in other words, it's just a shorthand for breaking it up into its components. See, that's not so bad. In fact, we can write this now as two different integrals. We have one that's got a 4 integral x dx, and if we integrate dx, x goes from 1 to 3. All right, and then we'll add that on to 3 times the integral y squared dy, and y goes from 1 to 4. And we can do these as normal. No big deal anymore. So we would get 4 times x squared on 2 evaluated from 1 to 3. And then over here we're going to get 3 times y cubed on 3 evaluated from 1 to 4. It's going to give me, let's see, this kind of cancels out. So I've got a 2. If I plug in 3, I'm going to get a 9 minus 1. That's the first one. And the second term is going to give me 3 and 3. Those cancel out. So I've got 4 cubed is 16 times 4 is 64, minus 1 cubed is 1. So that's equal to 2 and 8 is 16, plus 63 is equal to 79. And I guess if we're keeping units, this would have to be 79 joules. So there you go. Now it's about as easy of a line integral as you can have, but that's already harder than what you would see in the textbook, or maybe as hard as what you'd see in the textbook. It actually, the next step from here where we do have some path is not that much worse. I'm going to show this to you just so you see how it works out. If you take a higher level physics, you'll have to do it yourself, so it doesn't hurt to be exposed to it. We're just going to do another example. So suppose we do need to use the path. And the reason you would need to use that is you might get a mix of x, y, and or z showing up in the same term or in the same integral. Then what you do is you use the path to relate x, y, and z. And that always gives you a one-dimensional function. So as crazy as these things might look at first, at the end of the day, you're just going in one direction. These are always one-dimensional integrals, and they can always reduce to one-dimensional integrals. And all you're doing is first a dot product to make these into normal integrals, and then maybe you have to do a substitution using the limits so that you're in just one variable. So let me show you an example of that. So let's say that our force is equal to x squared I hat plus xy j hat. And we move our particle along the path y equals x from point 0, 0 to point 1, 1. And again, we'll assume everything's in the normal SI units. So the work is equal to the integral f dot dr. If we do our dot product, we're going to get two terms. The first one would be fx dx, the second one would be fy dy, and if we had any z components, then there would also be fc dz. We don't have any this time. Okay, so let's plug in what those components are. The first one has components of x squared times dx. No problem here, this is just fine. I'll leave off the limits for now, but we'll put them in later. The second one, we're going to have an integral of xy dy. Now that, as written, is a little bit of a problem because x depends on y. We're moving along some kind of path here, so there's an interrelationship between x and y. So let's use that to rewrite this integral. In particular, y is equal to x. So that also means that dy is equal to dx. Just like you would do a substitution for an integral, it's exactly what we're doing here, but we use the path as the substitution. Okay, so let's rewrite this. The first term stays exactly the same. The second term, it becomes, we're going to replace y with x, so this is x squared, and we replace the dy with dx. And hey, look at that, actually both of these terms are the same. So we could write that as 2 times x squared dx is, oh, and the limits of this would be the limits of x, which are 0 to 1. Your limits always match your variable here that you differentiate with, or that you integrate with. All right, anyway, so we're going to get 2 times x cubed on 3, evaluated from 0 to 1, is equal to 2/3. Now you might wonder, why don't we just, instead of saying y equals x, why don't we say x equals y? Oh, of course you can. It wouldn't change anything at all. This integral would then be the integral of y squared dy. No problem, because same limits. Gives you the same value. Has to. Alright, so that's probably a little bit more, I don't know, math heavy than you need at the moment. The point is so that you're not scared off as soon as you see a dot product show up in an integral. There won't be very much more of that in this first semester of physics, but in the second semester of physics you start to see that kind of thing again. And it's very easy to say, oh, that's too many symbols. No, don't worry about that. You just have to approach them systematically. And more importantly, figure out, what do these things actually mean? That's really the key here. What does this thing actually mean? Well, it means you've got some force acting on your object as you slide it along some path. Maybe it's windy, you know, maybe the wind is blowing and you're pushing a box along some wiggly path. How much work did the wind do? Okay, that's actually a problem we can answer, and this is the math to do it. All right, see you next time.